Oh yeah, I need to step. There we go. Welcome everyone. My name is Jan Lundgren. I am an associate professor at Mid Sweden University. I work with AI-supported sensor systems, and I have a research group working on this. And today we are going to hear from a defense from one of our PhD students, Thanh Tran. I will also like to present the grading committee and the opponent. But first, this is the written copy. If you haven't received it or you want one, you can contact me. It's also available on our DIVA portal, the national database in Sweden for publications. But with no further ado, I will start introducing the people involved today. So apart from our respondent, Thanh, we also have a grading committee. We can start there. We have Magnus Oskarsson joining in from University of Lund, where he works at the Department of Mathematics. Associate professor there. We also have assistant professor Sepide Pashami joining in from Halmstad University, working on the department of sensors for applied intelligence, and she also works at RISE. And thirdly, we are also joined by Daniel Ljung, associate professor at the Department of Systemteknik, System Engineering. Systemteknik is an old classic Swedish term. Maybe system engineering works at the Linköping University. And we also have Henrik Andersson joining us from the department, who is the backup from the faculty. But since we have all three grading committee members present, then those three will be the committee. And then moving on to the opponent today, that is Domenico Capriglioni, joining in from Department of Electrical and Information Engineering at the University of Cassino and Lazio in Italy. We have a program today. We have started with me just introducing everyone, and I will explain the format. Thanh will start by making a presentation of her thesis, what she has done, her outlooks on the science and everything. Then we will take a short break, where we will end the YouTube stream. So if you're watching us at YouTube right now, then that's the end of it. Then for those of you that have joined by Zoom, after a short break, we'll come back with the opposition. Associate Professor Capriglione will then lead the discussion with Thanh, and after that is done, then we let the grading committee ask their questions, and then finally the audience will have their chance. So if you are joining from the audience today from Zoom, it should be possible to pose questions in text. Also, if you want to ask a question directly after, that is also possible. After that, we will take a break where the grading committee and everyone involved will have a discussion meeting. These are the standard procedures, I would say. And then we will come back to the Zoom room for the decision. Yes. I hope I didn't forget anything. I usually forget to introduce myself, but today I remembered, so that's good. Then, Tan,
yes.
Tell us about your work.
Yes. Hello everyone. I'm Thanh Tran. I'm a PhD student at Mid Sweden University. I'm also a machine learning engineer at ASA Abloy Group. So today I would like to present my thesis regarding enhancing machine failure detection with artificial intelligence and sound analysis. So let's deep dive into my presentation. So we know that we are in Industry 4.0. It is the ongoing transformation of traditional manufacturing and industrial practice combined with modern smart technology. So we have hot topic with artificial intelligence, including machine learning and deep learning. And for application of the AI, we have audio, machine learning, application in image recognition, natural language processing, recommendation system, and many other areas. We also have the sound classification. It involves categorizing sound into predefined class based on characteristics, and it can be used in various domains like wildlife monitoring, bird song identification, or healthcare, like detect the heartbeat in pregnancy, as an image in the middle of the slide here. And we also have AI applied in industry. So the AI model can be quickly trained with existing either sounds or images. Then it can be connected to a smartphone or a computer and to be added to production line as an AI automated system. And it can help to detect product defect and improve efficiency, minimize false positive in production line. In this slide, I talk a little bit about the application of sound classification. Yes, as you know that we can apply in environmental sound classification with the classify urban sound, and it can be used in security system, can be used to predict maintenance, and also be used to differentiate animal sound. And it also have a very hot application in music classification that I think Spotify companies that apply it very much. So we can classify music, we can improve the recommendation algorithm, we can discover the chain of music, and which listener prefer to hear through data analysis or sound analysis. Yeah. Also, the hot topic regarding natural language classification involved in human speech classification, chatbots, virtual assistant, text-to-speech application. For example, in this image here, I saw that maybe a robot or an AI program can hear the sound of the bird singing. Then, with the trained AI model, we can detect what kind of that bird. Is it a parrot or is it an owl or any kind of bird? Yeah. Then in this slide, I'm talking about another application in industry. It's called machine failure detection system. So as you know, in industry, electronics have become more complex, and manual inspection is quite difficult and slow down production or time consuming, and technicians can feel fatigued and lead to missed defect, and it also increases the cost to repair it. And definitely because of it, so they have some traditional automated system to detect defect, and but it kind of like you traditional technique, a little bit outdated system, and may need to replace with new AI chain or advancing technology. And based on that thing, then we think about some innovative solutions that we can use AI power based on machine sound solution to solve it. And we can use either machine learning or deep learning to detect defects. And I think that it's a user-friendly approach because it can be used by manufacturing engineer and technician, and when we deploy it to the industry, we don't need an AI expert in the client, and it's easy changing a model, then just deploy it for client. Yeah. Then I think that regarding the results, efficiency in industry, it can reduce labor costs, and according to statistics were reported that it can reduce false positive by 20%, so it saves much money for factory or company. Yeah. And in this slide, I'm talking about noise suppression, or we can call it noise elimination or reduce noise in sound. So why do we need noise suppression? You know that recently researchers have paid much attention to the field of sound. So the sound usually contains silence, echo, and noise. It leads to difficulty in applying some state-of-the-art deep learning technique for sound classification. So we have a hypothesis that if we can locate and discard the redundant part, here I mean the noise of the sound, then the accuracy of the sound classification system will increase. Then I continue to talk give a little bit background about data augmentation. So why do we need data augmentation? Because audio augmentation is usually an essential step in pre-processing pipeline for deep learning model dealing with either audio data or image data, because it helps in improving model robustness, generalization, and overall performance. It also helps to prevent overfitting. It helps to improve the robustness of the model, because in real-world application, audio data can come from various sources and may contain noise and different accent or varying recording conditions. So augmentation technique like adding noise, changing pitch, or time stretching can make the model more robust to these variations. That's why it can improve the performance of the system as well. And we can talk that it also has a benefit regarding cost effective, because collecting and annotating new data can be expensive and time consuming. So audio augmentation provides a cost effective way to enlarge the data set, but without collect it manually. Yeah. So you can see a funny image here that why do we need data augmentation, but definitely it in image processing or object detection. That you see that in the image, the guy on the left side, then with the deep learning model or chain on the image, then it can detect hit rate 100% and 0 potato %. But when we flip the image 180 degrees, or we flip it vertically through x-axis, then it detects hit face and a potato. That's why we need to provide some data from augmentation, so the model can learn the variation. Yeah. It's just a funny image that I want to show you. Yeah. So we come to the thesis overview. So my thesis focuses on solving the following research question. The main research question was how can a machine failure detection system be developed using sound signal from Turing machine, especially when dealing with small real sound data set. And when we solve that main question, we have two sub-questions. One sub-question is which noise elimination technique are effective in enhancing the classification accuracy of machine failure detection system. And another one on the right side here, you see data augmentation. And which data augmentation methods are suitable and effective for extending and improving the performance of the classification model or machine failure detection system. Yeah. So you can see I have a graph here to show the main direction, and we got some branch, and we got two branches here that complement for the main research question. Yeah. The main research question in green color. Yeah. Then we identify knowledge gap in the field, that we know that manual detection have some limitation, that it is economically inefficient and labor intensive, because you need technicians, you need humans there, and you have to pay salary for them. Yeah. And also there are some challenges with previous research regarding data set limitation, and recognizing the significant role of real value detection in reducing machine downtime, and some challenges were posed by the limited availability of the drilling sound in data set. And another challenge regarding feature extraction and selection. So according to literature review, most previous research in the field has used manual feature extraction and selection, and it's tedious and it's potentially biased towards the one who decided to select feature. Yeah. And also, there is one big limitation, that the accuracy had not reached the accuracy that can be used to apply in industry. Even some use solely long short-term memory, or they use solely CNN, and it's still so limited accuracy. And the last but not least, it is the complexity of real-world sound. So sound in real work have complex waveform. It can be a combination of either noise and sound, and it makes classifications more challenging. For example, that may be a sound that you record the machine sound in the construction site. It can include the sound of the machine. It can include the sound of technicians talking to each other, and it can include maybe the water sound, something like this. Yeah. Therefore, we have some contribution to the field. So we have two main contributions. The first one regarding machine value detection. We have three approaches proposed for detecting machine values based on sound. And the first approach, and the second approach, and the third approach here, I will talk detail about them in the next slide. And the second contribution that we contribute in the research regarding noise elimination in sound. Yeah. So this table shows a list of papers. So my thesis was drawn from several published work, including the first paper in IEEE Access, the second one in Natural Scientific Reports, and we also present our research at various IEEE symposiums, such as IEEE SSCI in US, IEEE ISM in Italy, and IEEE SAS in Canada this year. And we also have open source repository available for some paper to facilitate reproduction and deployment of the proposed system. Yeah. Then I will continue to talk a little bit about data set we use. So in my research, I use multiple data sets, and our proposed method is usually validated across different data sets to improve the robustness, because it tests the method across various conditions, increasing confidence that it will perform well in different scenarios. And the findings are considered to be more general, making the research more universally applicable. And by using multiple data sets in my thesis, I strengthen the validity and generalizability of my methods and findings, making my research more impactful and widely applicable. And it's often seen as a strong point in academic research. So I will deep dive a little bit into technical part of my thesis. So I will present two sections, and the first section regarding machine value detection system. So why do we need machine value detection system? I talked a little bit before about the reason, because it involved in monitoring and analyzing sound produced by machinery to detect anomaly or fault or defect in the product and in machine. Sorry, not product, in machine. And it applied in industry to predict and prevent to prevent machinery breakdown, and thereby it saves cost and ensure safety at production site. For example, that it can including detecting fault in motors, turbines, or any rotating equipment. Or we got an use case in Sundsvall. It detects the drilling machine from Valmet AB, a company in Sundsvall. Yeah. So for techniques, it can involve time domain analysis, frequency domain analysis, and machine learning model or deep learning model to detect patterns or anomalies in the sound or vibration. So I said that in our research, also we validate our research in many data, but we also got a case study in Valmet AB data. Valmet AB is a company in Sundsvall that operates multiple drilling machines to drill thousands of small holes in metal plates. You can see in the image here. Yes, you see, and it has many small drill bits. Yeah. So this is when a machine is idle, and when the machine is drilling 1,000 holes on a metal plate, and it is a big figure of a drill bit. Then a healthy drill bit here, you see, and a broken drill bit. So the way that the company did before that, they have a technician stand near each drilling machine, and he turn off the drill machine every 10 minutes to check and replace any damaged drill bits. And definitely it time consuming, it labor intensive. So we propose a system that can detect broken drill bit, and I think that it's essential to reduce labor cost and also reduce production and time consuming as well. You don't want to turn on and turn off a machine each 10 minutes, and they probably have several machines, not only one. Yeah. So when we see it, we think about that vibration sensors are commonly used to detect machine failure. That's why we use sound intensive using vibration sensor, because for this UK, with each drilling machine, it consists of 90 or 120 drill bits, and it definitely costs much and complicated to mount the vibration of 90 or 120 sensor. Additionally, they use water. As you see in image, you see water here. They use it to remove dust from the metal plates. And if we use vibration sensor in extremely wet environment, it may have some trouble. Yeah. So we also see some traditional methods for machine failure detection system. So handcrafted feature extraction and selection, conventional classifier. But the recorded sound, we got content noise. And the waveform of sound are complex and short, usually around more than 20 milliseconds and more than 41 milliseconds. So it's very difficult if you even want to apply traditional methods to extract and select good feature manually. Then why we use deep learning? Yes, it's a question, but you know that deep learning and AI becomes a trend nowadays, and it's so it has been most extensively studied in recent years. So we decided to extract feature automatically using CNN, and it definitely has some benefit as it requires much human labor, require less human labor and knowledge, like hand design feature. And also CNN show good performance in image classification. So why we don't convert sound into image representation? For example, MEL spectrogram or log MEL spectrogram image, and we apply the similar techniques that or similar advanced technique for image into sound. Yeah. So in here I show the first proper method for machine failure detection system. So we have three classes of sound. For example, broken sound, normal sound, and irrelevant sound. So we do some pre-processing with high pass filter and low pass filter. because then we convert them on the sound to MEL spectrogram. Then we use VZZ19 to eject feature automatically, but we can eject many features. So we cannot use only feature to change the model. Definitely we find an algorithm to reduce the feature, and we only care about the feature that helpful for classifier, to change classifier. Then we change the classifier. So a little bit details for pre-processing that I use low-pass filter with pass band of 22,000 Hz, high-pass filter with a pass band of 1,000 Hz. Then I convert sound to MEL spectrogram. You see the MEL spectrogram in the image on the right side, on the right of the screen here. Then we eject feature. We use a pre-trained VZZ19 network and we eject feature from pooling file of the VZZ19, and after eject feature, we have 25,088 feature. It's very much. We don't need to use all of them because some feature maybe did not carry any meaningful weight. So we use feature selection. We perform feature selection with neighborhood component analysis, and after applying it, we reduce to 402 selected features that are valuable for changing a classifier. Then we train a model with these selected features. We try several model traditional approach like KNN, support vector machine, linear discriminant. And we got the results. We try many to change many classifiers to find the one that shows the best accuracy. And we got medium Gaussian support vector machine and quadratic support vector machine reach 80% of accuracy. Then in the second year, we continue to research deeper and deep dive into some more advanced technique in deep learning and to build a machine failure detection system with the hope that we can make the accuracy higher, make the system more suitable to apply in industry. So in the second approach, we use original sound, we convert into log MEL spectrogram. Then we propose a small CNN with only 3 convolutional layers and 2 pooling layers. But we have some trick in this CNN. I will talk about it in the next slide. Then from that CNN, we use long short-term memory and we use an attention layer. As you know, that attention layer helps us to pay attention into the parts that have meaningful knowledge in the sound. In here, you know that when the sound of a machine is broken, maybe it's a high peak that makes the sound abnormal. Then with the attention layer, we can pay attention to that part of the sound. Then we change a classifier. So we also recognize that we got a limitation regarding data set, that we have small data set. So we use some traditional data augmentation such as time shifting in the image on the left side, that we shift the sound 5 milliseconds to the right, then pass back to the original length. And we can use volume control, that we increase the volume that higher than the one that we recorded. In here, we use volume gain as 2 decibels. Then we convert sound to log MEL spectrogram. Yeah. It quite a change in sound signal processing recently. And yeah, as you see, that the MEL spectrogram displaying power in color. Yeah. So what you want instead of decibel, we can log scale. Then there are certainly different between each log MEL spectrogram. You see for anomaly sound and normal sound and irrelevant sound. And if you have chance to observe all anomaly sound in the data set, you can see that it looks different. And you observe all log MEL spectrogram image in normal sound, and you see that all of them look a little bit similar to this one, that the pattern looks similar. Yeah. Then we use a convolutional neural network using leaky rectifier linear units. And we propose architecture as you see in the image on the right side. So we use a pair batch normalization layer with leaky ReLU before and after convolutional layer to normalize feature and reduce overfitting. And although rectifier linear unit activation can compute faster than leaky rectifier linear unit, but to guarantee that the layer continue to learn when the slope of the rectifier linear unit is 0, we use leaky rectifier linear unit. Yeah. And we also know that the pitch of the audio changes as the real bit changes from the normal state to broken state. So we can use a layer of attention to pay attention to that anomaly. And after exact feature, using our small proposed CNN architecture with special design, we put it into long short-term memory with attention mechanism. And you know, long short-term memory is a recurrent neural network. It learns long-term dependency between time step of sequence data. Yeah, it's not a new thing, but it's very popular in time series analysis. I mean, long short-term memory. Yeah. Then we add an attention layer after long short-term memory, and finally, two fully connected layer in the end to predict class label. Then I will talk a little bit regarding the small CNN architecture we propose to extract feature and why we use leaky rectifier linear units for activation function instead of using rectifier linear units, because according to theory and we validate it through experiment, it improves the accuracy of the classification system. Because leaky rectifier linear unit have in leaky rectifier linear unit, the gradient weights are already updated with small slope. You see the formula of it in the left corner here. That it already it is 0.1. So it already updated with small slope. So it ensures that the layer continue to learn even when the slope of rectifier linear unit is 0. That's why it can avoid dead neuron, and it helps to mitigate the dying rectifier linear unit problem. And because with rectifier linear unit, sometimes neuron can get stuck during chaining and stop updating. And this part is particularly important for deeper network. And for attention mechanism, via experiment, my architecture also includes an attention mechanism, and the leaky rectifier linear unit activation function seem to work well in conjunction with the attention mechanism. Yeah. So in here, you move to the table, you see experiment we work with that. Firstly, if we use only CNN to classify sound, then we reach accuracy. In the first row here of the table, you see it's 69.95, almost 70%, still low. Then we add a long short-term memory. We use CNN to extract features, and we classify using long short-term memory, and we use leaky rectifier linear unit. We reach almost 87% of accuracy. Then when we use CNN long short-term memory with leaky rectifier linear units, but we add an attention layer to pay attention to the important part of the sound, then we got 92.35% of accuracy. It kind of like, I think here maybe more than 5% higher in accuracy. And when you see, we also compare that. We use CNN long short-term memory attention, but we use rectifier linear units as an activation function. And accuracy is only 90.16%, but with leaky rectifier linear units, accuracy is 92.35%. It means more than 2% increase. It validates our assumption that leaky rectifier linear units is working better in our case, and it validates our theory and assumption as well. And we continue in the third year with a little bit more advanced research, and we try to continue to improve the machine failure detection system. And we see that we try to improve with many ways to improve it, many techniques. But then we realize that with the small data sets, then we cannot reach higher accuracy after optimization. So we decided to investigate variational autoencoder to generate more synthetic drilling sound. So our proposed procedure is shown in this figure. First one, we use VAE, it means variational autoencoder, to generate more synthetic drilling sound from the original drilling sound as a data augmentation strategy. Then the original sound will combine with the generated sound from VAE to form the augmented data set. Then we use as normal that we still pre-processing with low-pass filter and high-pass filter. Then after pre-processing, we convert this sound into MEL spectrogram, and we just use a simple pre-trained deep learning model, AlexNet, very simple and very traditional, and we still reach very high accuracy. That we reach 94.12% of accuracy. Then we also compare if we just use AlexNet to classify sound and with the original data set that have only 134 sound divided into two data sets, normally and broken sound, then we reach 87.5% with AlexNet. But with the augmented data set that we have some synthesized sound from variational autoencoder that makes the data set bigger, then we reach the accuracy when we change the model up to 94.12%. Yeah. So yes, it's a long way. So I summarize 3 years research in this table. Yeah. That you see that the column on the left side, I show the level of the difficulty that when I started research, then I tried some traditional methods that very common, such as some pre-trained VGG19 or support vector machine that was there even from the time that maybe my supervisor did his PhD, something like this. And when the knowledge is extended, then I find a better way to do it in the second approach here, that we use log MEL spectrogram and we use CNN, propose a small CNN with some customized regarding activation function as leaky rectifier linear units, and we use attention layer, and we predict using long short-term memory, something like this. Then the level of knowledge is medium, I think. Yeah. Then later, when we realize that that we can nowadays we can generate image, we can generate sound, we can generate music. Now even that they can create some art or some picture, some image. Then we decided to apply it into our research, and we use VAE. It means variational autoencoder, and we change it successfully to generate synthesized sound and provide back into our data as a data augmentation methods. So the achievements and accomplishments that we address existing gap in the field by introducing some techniques. I think maybe it was new at the moment that we did it for sound classification and machine failure detection. And we use image representation of sound. It means MEL spectrogram and log MEL spectrogram. We propose some advanced sound classifier system, and we improve accuracy. That when you see that accuracy reach more than 90%, it has a high potential to apply directly into industry. And we have variational autoencoder chaining. We successfully chain a variational autoencoder for sound synthesis, and we providing a new avenue for data augmentation. And definitely, we have some cross-correlation analysis that I don't have time to present here, but it was written in my thesis. Yeah. Then I will move to the second contribution that of my thesis. It's regarding the noise sound, or you can call it noise suppression or noise elimination. So we separate sound into STFT frame to eliminate sound noise frame. So we still raise a question, why do we need to eliminate noise in sound? Because when we do the main stuff regarding sound classification for machine failure detection system, we realize that the noise in sound that make the sound classification accuracy is low. So we think that if we can eliminate noise in sound, it will improve the accuracy of machine fault detection system. It also reduces cost because accurate sound classification can minimize downtime and maintenance costs in manufacturing. And it's also work in real-world complexity that addressing noise have tackled the complexity of the real-world sound data set. Yeah. We propose a sound classified system that including two phases. The first phase is the image above. It called the chaining phase. It involved with audio separation and labeling STFT frame. So this frame, we separate each sound into many STFT frames. And these frames are used to chain a pre-chain network, as shown in the chaining phase of the figure. And in labeling, we label the frame we separate from each sound into either clean class or noise class. Noise class here we get involved with echo, silent, and noise STFT frame. And we need to label it manually. It called data processing, and for data processing, pre-processing, we still need to do it manually. Yeah. Then the frames are used to chain some pre-chain models such as Google Net, VCC 16, VCC 19, many. I did not want to list all of them here because we want to see the best classifier model that work for our methods. Then for the classified, the prediction phase below for the classification task is so that when the testing sound get into our system, it will be separated into many overlapping STFT frames, and when it goes through our chain classifier, it will be classified into 20 classes, and we also add one class that did not exist in the data set that will absorb all the noisy frame. In image above you see, for example, echo, silence, or noise. So with that proper methods, if you see on the table on the right side, after classify it, we have accuracy of 94% for the proper methods, but for conventional methods, we have only accuracy of 55%. So what is the proper method that we separate each sound into multiple overlap STFT frame, and we change a classifier to classify them. And after separate the sound into STFT frame, we separate 896 sound into 4,827 STFT frame. And then we divide the data set and use pre-chain network to rechain them. Yeah. But for conventional methods, that each sound we convert into only one STFT image. It is a common approach in sound processing, that for each sound they convert only in one STFT image. Then with the same condition, with 896 sound, we convert only 896 STFT image. Then when we change a classifier for it, the accuracy reaches only 55%, much lower than using our proper methods. So it go to the end and I talk about achievement of that part. So we develop a new way to categorize sound frame into 4 types: silent, clean, noise, and echo effect. We introduce the amplitude waveform pitch sound representation to locate the component of the sound. And we create a sound classification system that use sound separation and STFT frame. And we also successfully label STFT frame beyond frame type. And we improving the classification accuracy. Yeah. And also through this research, we have effective learning data preparation, that we utilize sound from own classes of the dataset FSD noisy 18K for data preparation. Yeah. So I'm moving to conclusion. Yes, definitely I want to talk more, but due to limited time, I have to move to the conclusion. And if you want to know more, then feel free to contact me. So I will revisit the research questions so you don't forget what I did, what is my main focus. So still the main question that we want to build a machine failure detection system based on sound from machine. And the sub-question that complement for our main research question is which noise elimination technique are effective in enhancing the classification accuracy. And the third sub-question is which data augmentation methods are suitable and effective for extending and improving the performance of small real sound dataset. Yeah. So in conclusion, we addressing the we focus on developing a machine failure detection system using sound signal from drilling machine and importance of real failure detection in reducing machine downtime, and we addressing challenge due to limited availability of drilling sound in dataset. Yeah. And in conclusion, we answer the first question about building a machine failure detection system, and with 3 approach. The first approach, we convert sound into MEL spectrogram. We check feature using VZZ. We select good feature using NCA. We classify using traditional approach using support vector machine. And the second method, we convert sound into log MEL spectrogram. And we classify using CNN with leaky rectifier linear unit combined with attention-based long short-term memory. And the last method, the third method, we addressing the research question. The first research question and the third research question regarding augmentation of sound dataset as well, because we use variational autoencoder to generate 96 novel drilling sound to complement to the original data, and we achieve high accuracy for building a classification system based on it. Yeah. And for addressing the second research question regarding eliminate acoustic noise in sound to improve the robustness of the sound classification system, then we separate sound in STFT frame and we label them manually as clean or noise, and we classify that using pre-chain VZZ19. Yeah. Then I, since it come to the end, I talk about future technique and chain. So for machine learning and AI, I think in the future, if we continue with this research, we can definitely look at some chain for learning, and pre-chain model could be adapted for different type of machinery, and it also reducing the need for extensive data collection. Also that as a chain nowadays, especially model like BERT or ChatGPT or large language model, and with the data set grow and computational resources available, then definitely we can look into it. And we also need feedback loop by, we continue to collect new data and retrain the model with the new data to ensure it stay up to date and improve over time. And definitely another chain in AI nowadays regarding AI in edge computing. So for machine failure detection, algorithm can run directly on IoT device, and it also need to consider regarding energy efficiency. Yeah. And another thing, also a chain that they want to make the AI more transparent. So it needs to include human in the loop, that we need expert feedback. Then with the expect that the system could incorporate expert feedback to continuously improve performance model. And if we can make AI more transparent, it could help engineers understand the AI's decision-making process. Yeah. And the last but not least, it can regarding real-time monitoring and cloud integration with cloud analytics and 5G connectivity. Definitely it's not in my knowledge, but I know it's a trend now. Yeah. So thank you. I think my presentation come to the end. Yeah, thank you.
Yes, thank you, Tan. And with that, we are closing the YouTube part, the YouTube session. And we need a slight technical break. How many minutes do we need? 10 minutes. So we will reconvene then at about 10 a.m. Yes.
Thank you.
See you then.